In this problem, what we're looking at is this linearly elastic material block. It's got a known Young's modulus E and a known Poisson's ratio of nu. We're fitting this block between two smooth walls. It's a fairly tight fit, there's no gap. And then we load it up with a compressive axial stress there of sigma naught in X. As a result, though, of putting the axial stress on there, we generate a component of stress in the y direction because we're pressing the block against the wall due to the Poisson effect. What we want to figure out from this is what is the stress that is generated there at the wall, what's the change in the length delta A of the block, and what's the change in thickness, that is the change in the dimension there in Z. I'm going to write down our three equations from Hooke's law. So I have the usual sigma x minus nu times the quantity sigma y plus sigma z all divided by E, then adding on the thermal term. The strain of y, recall that's 1 over E sigma y, minus nu the quantity sigma x plus sigma z plus the thermal term. And likewise, for the z direction, we have 1 over E sigma z minus nu sigma x plus sigma y plus the thermal term. We're not seeing any change in temperature here, so we can drop out these terms. The case is for plane stress, so there's no stress in Z. So this term is gone, and this term is gone as well as this one here. The things that we know about this is that we can write epsilon x in terms of the change in A. So it's delta A over A, and we don't know that. That's what we're trying to find. We know that epsilon y is equal to a 0 because we've got the wall. Epsilon z is equal to delta t over t. That again is something we're trying to find because we don't know delta t. Also note that sigma x here is minus sigma naught. It's a minus sign because it's a compressive component of stress. And as I've already indicated on here, sigma z is a 0 and sigma y is something that we're trying to find. So from these three equations, we're going to pull off our three unknowns. So the first equation says we have delta A over A is equal to 1 over E minus sigma naught minus nu sigma y. I have that a 0 on the left-hand side for epsilon y is equal to 1 over E sigma y, which we're trying to find, minus nu sigma x. So from this, we see that sigma y is equal to nu sigma x. So that's a minus nu sigma naught. And so therefore, based on the second equation, we can write delta A over A as being 1 over E minus sigma naught plus nu squared sigma naught as this. So from this we see that delta A is equal to A over E sigma naught minus 1 plus nu squared. And then finally from the third equation we see here that delta T over T is equal to minus nu sigma x plus sigma y. On the right hand side, therefore, we have minus nu sigma x we saw was minus sigma naught. Sigma y we saw was minus nu sigma naught. So in the end, what we have here is nu sigma naught times 1 plus nu. And so therefore, the change in thickness of this is to multiply the original thickness times sigma naught nu 1 plus nu as that. So it's just a matter of using our three Hooke's law equations, knowing what our relationships are, and then from that we enforce the fact we got the wall, so there's no strain in Y. We know what stress we're applying in X, it's compressive, and we're able to calculate effectively those two components of strain and the one component of stress from Hooke's law.